Good morning, everyone. My name is Dan McEvoy, and I'm a climatologist with the Western Regional Climate Center and Desert Research Institute. Today, I'm going to present some of our results from our study that looked at what future changes in evaporative demand could mean for seasonal fire danger and long-term droughts in California and Nevada. The work was funded through California Nevada Climate Applications Program, CNAP, which is the NOAA RESA, and also with support from NIDIS, the National Integrated Drought Information System. I wanted to start by establishing the connection between reference evapotranspiration and drought and wildfire. Reference ET is just one measure of atmospheric evaporative demand, and it's been traditionally used in agriculture to estimate crop water use. But here we use it as a measure of atmospheric drying, which is not specific to a crop type or any land surface information. We can use the accumulated excess evaporative demand to monitor drought in a similar way that we use accumulated precipitation deficits. And the weather drivers of reference ET, which are temperature, wind speed, humidity, and solar radiation, also happen to be the primary variables used to track wildfire danger. So when we have periods of above normal evaporative demand during already dry conditions, that will act to suck remaining moisture out of the dead and live vegetation, leading to more enhanced or elevated wildfire danger. One piece of today's talk is going to focus on the Evaporative Demand Drought Index, or EDDI, which was developed several years ago to fill a gap in drought monitoring. EDDI has become widely used across the United States for drought monitoring, but in the past few years, we've been investigating the applications of EDDI for tracking wildfire danger. And high EDDI values have correlated very strongly with locations of recent major California wildfires, as seen in the graph here. EDDI values at or above the 95th percentile were found at the start of both the camp and the car fires when considering the shorter timescales or those accumulation periods. So in the top left map, we're showing a 1-month EDDI for November 8th, which is based on the 30-day reference ET accumulation ending on November 8th, and then the percentiles are based on all the other 30-day periods ending on November 8th. And if we look at the time series on the bottom right, it shows that with both the car and the campfires, the EDDI values ramped up in the weeks leading to the fires and peaked very close to the fire start dates. The vertical lines there denote the start dates of the two fires. Now, this next set of maps is using predictive service area boundaries. Those are the filled polygons. These areas they're a management unit used by the National Interagency Fire Center and also Predictive Services for monitoring and forecasting fire danger, as well as allocating resources for fire suppression. And the shading shows the fraction of the total burned area in each polygon that occurred coincident with extreme EDDI values. We can see a number of regions with 15 to 30% of the burned area occurring when EDDI was greater than 2. And the likelihood of, on any given day, of seeing an extreme EDDI value greater than 2 is only about 2%. The areas in Nevada and Southeast California with lower fractions are typically much more fuel limited with far less timber than the other regions. I also want to note that prior to the study, there was another study we had that focused on future projections, that focused on historical EDDI, and we spent time introducing EDDI to the fire management community, and Predictive Services began using EDDI during the 2018 fire season. In-season fire danger is one side of the story for this study. The other side of that I'll be talking about today is on the effects of evaporative demand on multi-year droughts, which arguably have the greatest impacts to water resources in our region. Our last extreme multi-year drought was one for the record books, and it lasted about 4 years, from about 2012 to 2016. The map on the left shows a 3-year standardized precipitation index ending September 2015. And this considers precipitation only, and we do see some extreme values, but precipitation wasn't the only story, as this was a hot drought. And the map on the right now shows the SPEI, which uses the difference between precipitation and evaporative demand, and we see a much more widespread extreme values throughout the region. And one of the feedbacks from this drought was the massive tree die-offs in the central and southern Sierra Nevada that led to huge dead fuel loads. And some of that is burned this year in the massive fires we saw in the central and southern Sierra Nevada this past summer and fall. So looking back at 3-year droughts since the start of the 20th century through the lens of SPI and SPEI, we see some interesting things here. And these results are for 4 predictive service areas. 3 of them are in California, and then on the bottom we also have the Humboldt Basin, which is in northern Nevada. Here the green is SPI and the orange is SPEI. I'm also showing the 5th percentile line to highlight the extreme events. And so both indices tend to agree on the major dry and wet periods, but differences show up in the severity of the droughts. We do see more separation between SPI and SPEI since about the start of the 21st century, with SPEI showing more severe droughts. It's interesting to see that in all the regions except for the Mid-Coast to Mendocino region, SPEI shows the most severe drought on record during the 2012 to 2016 period, while SPI does not show that. So this indicates that looking at the precipitation alone is not enough to quantify the impacts of these hot droughts with high evaporative demand. For the study, we wanted to look at how extremes in short-term with in-season eddy and also long-term SPI and SPEI changes throughout the future. So I used a downscaled global climate projections based on the LOCA methods developed at the Scripps Institute of Oceanography. And this consisted of a 7-model ensemble from which I computed the evaporative demand and also used the precipitation data. The green polygons in the upper left panel show the 4 predictive service areas that I focused on for the study. And the future eddy and SPEI are all relative to the baseline period of 1950 to 2019, and also the three future periods denoted there were used. So first I want to show the seasonal changes in evaporative demand and precipitation across the region. These maps show the average change over the late century period relative to the baseline. And for evaporative demand, we see 10 to 20% or greater increases that are consistent across all 4 seasons and also spatially across the whole region. The precipitation story is quite a bit different, where we see winters get wetter with a 50% or more increase for parts of Nevada. The shoulder seasons of spring and autumn get drier throughout California and southern Nevada. So this alone has implications for a longer fire season, as summer is already the dry season and the peak of the fire season. This here is an example of the future projections unfolding right in front of our eyes. So we've already been seeing an increasing trend in seasonal evaporative demand since 1979, and this year again set records for the region. When we looked at the September through November total evaporative demand, 2020 was the highest on record in both states. And the California record really stands out as it's substantially greater than the previous record. So this hot and dry atmosphere no doubt contributed to the extreme fire season we saw this year in California. And I just want to give a quick shameless plug here for Climate Engine, which is the web application I used to create these figures on this slide. And I strongly encourage you to check it out if you're looking for easy ways to visualize weather, climate, or remote sensing data with updated data in near real time. Next, we want to look at what was driving those increases in seasonal evaporative demand. This figure is showing the autumn late century changes in evaporative demand and precipitation on the top row, and then the 4 drivers of evaporative demand in the bottom rows. Each dot is then a different LOCA model. And then these results were averaged over the 4 predictive service areas, and I'm going to focus on the Humboldt Basin results today. So we see that all models are showing increased evaporative demand. The precipitation signal isn't as clear, with about half of the models showing wetter autumns and the other half show drier autumns. The increased temperature signal is quite large, and we see changes of about 5 to 7 degrees Celsius. And the warmer atmosphere is in turn driving up the specific humidity, which we also see increasing. Solar radiation signal is weak, with some increasing and some decreasing, and the wind speed is found to be decreasing. So based on this alone, it would appear that the temperature is the main driver of the increased evaporative demand, but we need to do a sensitivity analysis to quantify that is actually the case. So to further examine which driver was playing the biggest role in increasing evaporative demand, we ran a very simple sensitivity experiment. And this graph is now showing the average autumn evaporative demand anomaly in the black bars and the contributions from each driver in the other colors. The first thing we see is that the orange temperature bar is always higher than the black evaporative demand bars, which tells us that the increased temperatures are having a positive contribution to the total ETO anomaly. We can also see somewhat sizable green bars in the negative direction, which is the specific humidity. And the increased humidity will act to decrease evaporative demand, and we see a negative contribution. So what it comes down to is that the increased temperatures are also increasing the saturation vapor pressure, and that's outpacing the smaller decreases in actual vapor pressure. And therefore, the vapor pressure deficit term in the evaporative demand equation is still increasing and driving up the evaporative demand. You can see that there was very little contribution from wind speed and solar radiation, and you could actually barely even see the color bars there. Next, we're looking at the average number of days for each summer and autumn where the 2-week eddy exceeds the 95th percentile at our 4 predictive service areas. For reference, during the base period, we would expect to see about 4 or 5 days per season above this threshold. And the 3 columns going left to right show the progression from early to late century. The open circles and triangles show the spread of the 7 models, and then the filled shapes are the ensemble medians. And what we see is that all models are agreeing on the increasing frequency of the extreme 2-week eddy, which is consistent with the seasonal increase that I showed earlier. This shows that during the next 20 years, our early century period, many of the models already show a doubling of the number of extreme days. And then by late century, we see up to a 10-fold increase in summer, and then up to a 6-fold increase in autumn. So major changes by the end of the century in extreme eddy days. And the results on the previous slide, what they really translate into are eddy maps like the one shown here are going to become much more common in the future. This is from mid-September of this year, and we see a large swath of reds indicating values above the 95th percentile. And so this was during our peak fire season this year, where we had a number of very large wildfires burning throughout the region. Now I'm going to shift gears a bit and look at the changes in the frequency of long-term droughts. And as I mentioned earlier, these multi-year droughts, they have the greatest impact to our region. And this is when we start to see things like reservoirs emptying and also major ecosystem impacts like tree die-offs. And the long-term droughts also create more dry and dead fuels for wildfires. And this graph, this is very similar to the eddy graph I showed earlier, a couple slides back, but now we're looking at SPI, which is just the precip, and SPEI. And instead of looking at the number of days in a season, like with the eddy graph, we're now looking at the change in the number of years below the 5th percentile, since we're looking at these multi-year droughts. At our most water-limited locations, and this is where the annual evaporative demand far exceeds the annual precipitation, we see strong increases in extreme SPEI droughts. For the South Coast and Humboldt Basin, about 60 to 70% of the years by the late century show extreme drought. And in contrast to this, we see minimal changes in the SPI precipitation-only droughts. You'll remember I showed increased winter precipitation, which accounts for the bulk of annual precipitation for these regions. So the take-home messages from this are that the elevated evaporative demand at short timescales, plus the lingering long-term droughts impacts, plus the late onset of fall precipitation during recent California fire seasons leads to increased fire potential and likely a glimpse into our future fire seasons. For the projections results, we saw the steady increase in evaporative demand that was largely driven by the increased temperatures. We saw more extreme short timescale eddy values that will lead to more days with higher fire danger. And the decreasing fall precipitation in California will amplify the increased fire potential. For the multi-year droughts, we saw major increases in the projected SPEI droughts for the water-limited hydroclimates, and a much less pronounced changes in the more energy-limited hydroclimates like the Sierra Nevada and the north coast of California. And one last thing I want to mention is the State of Nevada Climate Initiative. This was a report. It was just released at the beginning of December 2020, and I was lucky enough to be a part of the team that produced the Climate Change in Nevada chapter, along with others from DRI, UNLV, UNR, and Scripps. This climate strategy is intended to help state progress towards more climate change action and policy. And I feel very proud to have been able to contribute to the drought and fire danger portions of this chapter and some of the SPEI and eddy results used in the report I'm showing here. And I strongly encourage everyone to check it out if you haven't already done so. The link is listed right there at the top of the slide. And with that, thank you for listening today, and I look forward to seeing everyone at the live Q&A session. Thanks.